Vincenzo. Mantova will tell about surreal numbers and Transseries. Thank you. Let's start.
Thank you. Okay, thank you very much for the invitation and for everything. I mean, like everybody, it's terrible that I can't be there in person, but it is what it is. Okay, so this is this talk is more of an overview about what we want to talk about in this course, surreal numbers and Transseries, which is part of the longer course Transseries and asymptotic analysis. Okay, and actually I'm teaching this with Alessandro Berarducci. I was supposed to be there in person and do some of the in-person whiteboard or blackboard stuff, but of course it's going to be online. So it was going to be a bit different than what we were hoping to do. Anyway, let's talk about the mathematics. So I assume that there's plenty of, that there are people who have maybe never heard of surreal numbers at all, possibly. So we'll see. Please stop me if things don't make sense anymore. Okay. So first, let's start with a general, panorama of what the two key things are. One is Conway's field of surreal numbers. So it's if you've never seen it and you're not familiar with it a lot, it's a huge field. It's a large ordered class. When I say class, it's because it's a proper class in the sense of set theory. It's not a set. It contains, in the words of Conway, all numbers great and small. So it certainly contains all the real numbers, the ones we all know, square root of 2, pi, etc. But it also contains a copy of the ordinal numbers. And these are some silly examples. I mean, the ordinal number omega, this is going to reappear later a lot. This is the smallest infinite ordinal number. So it's the first ordinal number you get after the natural numbers. It also contains other stuff like epsilon 0, which logicians would know, omega 1, that's actually the cardinal omega 1, so it's the least uncountable ordinal, but everything is in there. And sort of the funny thing is that these are all inside a large field, a field which is real closed. So it's a field, so for example, the inverse of omega is another surreal number, but you can also take square roots, for example, and for example, square root of omega minus pi is a surreal number. All right, and what's more, I mean, the small structure is not just a field. There is a canonical function. Well, there are canonical functions log and exp, one inverse of each other, which behave in a precise way that I will explain a bit more later. Behave exactly like log and exp on the real line. Okay, and so for example, you can take the logarithm of the ordinal omega, you can take omega to the square root of 2 and do other stuff. Okay, so that's one part of the picture, the surreal number. So keep this vague image in mind at least. It's a huge line, which is a real closed field, so it's very similar to the real numbers. And the other side of the picture is the one that Lau was talking about on Tuesday, which are Transseries. Okay, and so this is an example of Transseries or Transseries. It's some kind of transfinite sum of decreasing terms, possibly with some real coefficients, which may involve exponentials and logarithms of the variable x. Okay, so these are expansions in one variable. I think that now this is more familiar with the audience, and this is transfinite in the sense that, for example, this one has length omega plus 2, so there is an infinite sum here, and then there are also 2 extra terms at the end, and you can have more complicated sums like this. Okay, now constructing, Lau said on Tuesday that constructing Transseries is a delicate process because you have to put restrictions on which kind of sums you allow and which kind of exponents. And so you have to be careful about it. And it gets tricky to define Transseries in a talk in a proper way. But in a sense, we're going to do it passing through surreal numbers. But that's also a challenge. Okay, in any case, when we talk about field of Transseries, I'm using this convention of using the letter T for the logarithmic exponential series, or at least Rayleigh Transseries that are exactly, again, the ones that I was talking about, which have a nice model theory. For example, they are closed-end integration, taking solutions of these differential polynomials. More precisely, I was explaining to us on Tuesday that this particular field of Transseries, so this particular collection of formal sums like these ones, satisfies the intermediate value property for differential polynomials. So it's very nice. Okay. Now the general claim, and it's sort of the core of the course, is showing, explaining in what sense the field of serial numbers is on its own also a field of Transseries. Okay, a much bigger one, because as I said, it's a proper class. It contains all these very large numbers like this omega 1, which does contain a copy of T. Okay, and this is in light of a much larger conjecture, which is not going to be quite in the course, but I'm going to mention it, and maybe we will see some easy parts of it. And it's that actually the serial numbers are isomorphic not just to Transseries, which are series with exponent log, but to hyperseries. And that hyperseries are even more nested expressions where you have more functions which want to represent transfinite iterations of exponent log. Okay, and this is going to be something I'm going to talk about again at the very end of the talk. Because now there has been a lot of progress on this, not so much by me, but by people, but it's still things are still moving. It's very recent. Okay, so let's try now to see some more details. Okay, so this is the guy I want to talk about the most, and eventually I'm going to tell you who is T inside the serial numbers, and hopefully it will make sense to everybody. Okay. So, serial numbers, how do you define them? Well, there are several ways, but the way I prefer is this one. You have to think that the serial numbers form a very long line, and the way you create it, so you generate serial numbers, is to inductively filling all possible gaps. So you start at the beginning. And Conway likes to talk about day 0. So at day 0, at the beginning, you have nothing. So the first gap you have to fill is just nothing. So there's only one point you want to add to your structure, and that's how you start. So you start with the point 0, and that's the first thing you have. Then on day 1, you continue, you say, well, now I have 0 on a line containing 1 point, and now I have 2 gaps, one on the left and one on the right. So I add 2 points, which I'm going to call for now -1 and 1, -1 to the left and 1 on the right. Okay, so the thing that should, at least it's more natural. And these names are going to justify why we're choosing -1 and 1 here eventually. But let's stick with these because it's, at least I can name the points. Okay, now I have 3 points, which means I have 5 gaps. I can stay, there's a gap to the left of -1, there's the gap between -1 and 0, a gap between 0 and 1, and then a gap to the right of 1. So what we do is we add, 4 points, 4 gaps. I add 4 new points, 1 here to the left of -1, 1 here between -1 and 0, then 1/2 is between 0 and 1, and 2 here. And I guess now you get the procedure. I just continue. Okay, now I have 7 points. 7 points give me 1, 2, 3, 4. I have to count them. 1, 2, 3, 4, 5, 6, 7, 8 gaps. It should be twice as many as before. So I add 8 points again on the 3rd day. And I keep going. Now after the 3, you just continue this over every natural number. And you already get a nice structure. You get the density in order already after doing the finite, after going on for finite many days. But then you continue. And then on the omega, what you do is, for example, you notice that between 0 and all these serial numbers I constructed here, there's going to be a gap. Okay, and that gap is going to be called 1 over omega. And or I can keep going to the right, and I'm going to have another gap here, which is going to be greater than all these serial numbers, which are called 1, 2, 3, 4, 5, like all the natural numbers. Okay, but then you don't stop there, you keep going. So if I, for example, I can start from omega, I can take the first gap to the right of omega, that would be omega plus 1, that would be its name. And then I do it again, I take omega plus 2, and then I keep iterating over every ordinal. So I'm going to have day omega 2 omega, epsilon 0 omega 1. You just continue. And you keep doing this over all ordinals, which is why you get a proper class in the end. Okay. And now you have to look at the structure, right? You have to think now that this is a single line. So I'm representing this as a tree because it's more legible in this way to see how we constructed it. And we do use this tree structure. But ultimately, the first thing we want to see is this is a line, okay, with points all over the place. Okay. Now something that makes more sense from other theories, but the statement is also should make sense to everybody. We do get a dense order in the sense that between any 2 points, any 2 surreal numbers, there's going to be another one in between. But more strongly, this is a saturated order. Saturated just means whenever you take 2 sets of points, A and B, 2 subsets of the serial numbers, such that I forgot something crucial. Take 2 subsets, A and B, such that every point of A is less than every point of B. So let me add a less than here. Okay, it's not very legible. Okay. If you have this, and these are 2 sets, then you can find a serial number which falls in between. And the intuition is, I mean, for example, I could take A to be this set, this could be A, this could be B, some bunch of points. As long as it is a set of points and not a proper class, then I can find a serial number which falls between A and B. Okay, in this case, for example, -1 over 8, which is not visible in this picture, would be one potential number here. Okay, so you have this situation that it's very dense. However, you take 2 sets of points, you can find something in between. Actually, and this is now crucial, and I should highlight this. Do I highlight? Oh, yes. That not only you can find a point between any 2 sets A and B, but you can find the youngest point. Youngest means that the day the point was born, so the day in which this serial number appears in the picture is as small as possible. Okay, and this youngest guy is unique. Okay, and we're going to use this on the next slide immediately. Okay, and then another comment. This is now more technical. You don't need to really think too much about it. I've written prepared the talk in a way to avoid these technicalities as much as I could. If you want to know more concretely how we represent the serial number, so how we construct it in a more saturated way, if you care about it, I do. I prefer to think of them like this. This is the encoding of Gonsher. And the idea is that you look at this tree. So the way you look at the way the serial numbers appeared in the tree, and you label these two edges with plus and minus. Plus if you're going to the right, and minus if you go to the left. And now to identify any serial number in this tree, I have to give you a sequence of plus and minuses that tell me where to go. So you tell me the ordinal alpha, which will be the birthday of your serial number. That's the terminology that people use. And that would tell me at which level I am in this tree. And then the sequence of plus and minuses tell me where to go. And you should see, I mean, at least from this picture, you should see that every serial number is identified precisely by one of these sequences. So in practice, what Gonsher does, for example, is that the definition of a serial number, the serial number is a sequence of plus and minuses indexed by some ordinal. That would be the definition. But that's the picture, that we want to have in mind of these numbers appearing and every time filling the gaps between the previous numbers that you already have, but done transparently many times, so you get something really dense. Okay. I hope that this makes sense so far. Any questions? Any doubts? Okay. Yeah, okay. So I'm going to continue. And now let's go to the now more interesting stuff, okay? Because now this is just a boring line. It doesn't have any structures. It doesn't have any structure. What does it have to do with Transseries? I mean, now the point is, since we have this tree structure here, we know we can take the youngest elements, etc. We can define functions. Okay, and now I'm not going to give you too many details here because then it gets complicated quickly, actually. So let's start from the key information is, first, the serial numbers are generated by induction. So every serial number has a birthday. The birthday is an ordinal, and so you can do induction over the birthday. Okay, so the first serial number is 0, and then you have the other ones. And then you have this property. This is crucial. If you take two sets, again, I keep forgetting to say, if you take two sets of serial numbers, such as the set A is entirely less than the set B, then there is a unique youngest serial number which sits between A and B. Okay, with these two pieces of information, I can define, for example, the first non-trivial function that one defines, I mean, Conway defines in his book, is this one. Whenever I take two serial numbers, I define the sum, x and y, to be the youngest serial number such that, well, I want some conditions. And now the condition here is essentially that this sum is increasing in both arguments. So what I say is that x plus y, I want it to be greater than, for example, let's look at only this term. So let's look at this one only. So x plus y, we want it to be greater than x prime plus y. In general, whenever x prime is less than x, but since we're going by induction, I'm just asking, I want x plus y to be greater than x prime plus y for all x prime which are younger than x and such that x prime is less than x. Okay, because what's happening here is that by induction, I can assume that I already know the value of this function. I define it. And now I just say I can compute this value and also these other ones because these x prime, y prime, x double prime, y double prime are younger than respectively x and y. So I know these values, and then these values form a set because the numbers younger than x and y form a set. Because at that stage you haven't built so many to get a proper class ready. This is more of a technicality. I mean, the point is you can do this. You get two sets, one on the left, one on the right. You can verify inductively that they are placed in the right way. So everything that appears here in the set A is actually less than everything on this side. This is an easy induction, which I'm not going to do now, of course. This is more of a detail to how you prove things. And now I use this other property. Okay, I have two sets, A and B, and there is a youngest element which sits in between. And I define x plus y to be that element. Okay, so the smallest guy you can plug in here, satisfying this condition which we expect. I mean, we want the sum over an order, so we want to get an ordered group in the end. That's the kind of structure we want. So at least we want this to be increasing in both arguments. And now we get a nice structure. So for example, you can immediately see, it should be immediate from the way the definition is written, is that this is symmetric in the sense that x plus y is equal to y plus x. Okay, because this definition doesn't put any, there's no difference between x and y here. So by induction, if you assume by induction that these guys are symmetric, then the end result is going to be symmetric as well. Okay, but more generally, what you get is a divisible order of the Billion group. Of course, you have to prove it. But for example, I mean, now the fact that this is a group can justify these names, these labels I was choosing on the tree. For example, you can prove that x plus 0 is equal to x. And in this case, this is another thing you can prove easily. You can prove it by induction directly, and the proof is easy. So what's happening here for this particular equality is that you try to apply this definition, x plus y. Now you have x and 0 here. And what happens is that nothing is younger than 0. So to define x plus 0, you're only doing the induction on the birthday of x. Okay, because 0 is already youngest, is the youngest possible, and there's nothing else before. And so now you verify, and then now you plug this information into this formula. It means you can drop all the references to y prime here and y double prime because they're younger. And you assume by induction that x prime plus 0 is equal to x prime. And you work it out, and it's exercise, so to say. You can verify that x plus 0, that the youngest guy between whatever you find here and the stuff you find here is actually x itself, almost just by looking at the tree we had on the previous slide. Okay, and then you can do more computations, like -1 plus 1 is equal to 0, 1/2 plus 1/2 is equal to 1, and these are all computations you can do by hand. The point is, there is a canonical nice way of defining functions by using these inductive constructions of surreal numbers, and this property that there's always space where to find a new point, and under good conditions, so in this situation in particular, you can find that there's always a unique youngest choice you can make for a guy sitting in this place. Okay, so this is what you get so far. This is how you get plus, and then you can get other functions, and I will spare you, trying to make sense of any of them. So you can define the product of two surreal numbers. The formula is a bit more complicated, but it's similar. It's not worth it writing it right now. You can define an exponential function, and actually you can also define every analytic function on the real, so every real analytic function, with one caveat. These analytic functions, the way they're defined traditionally, so the ones I'm referring to right now, are only on the convex hull of the real numbers. Okay, so when I'm talking about, so what I'm saying here is, if you take a real analytic function on the real, so maybe on some intervals inside the real line, then I can extend this to the surreal numbers which are in the convex hull of that interval, okay, not further away. So if I take a random analytic function, I won't be able to automatically to define its value in the ordinal omega, because omega is greater than all real numbers. It's outside of the convex hull. So this is not something I can do for free. There's extra work to do. Okay, so there is a question in the chat. Does being younger coincide with the order in the group? That's a very good question. I should point this out, because otherwise things will get really confusing. So let me remind you, we had 0, -1 on the left, 1 on the right. And then, for example, I had 1/2 here and 2 here. So what's happening in this particular example is that 1 is younger than both 1/2 and 2. Okay, so while of course 1/2 is less than 1 and is less than 2. So what I should do in this picture is to say that the ordering, the line, is meant to be just the projection of this point. So you flatten the tree, and that's how you picture the total order, the order in the sense of this line. So this is the picture to have in mind. And whereas the birthday is the vertical order, so it's how deep you go in the tree. So it's like two orthogonal orders, I would say. So one is horizontal and one is vertical. I hope that that makes sense enough to. Great. Okay. Okay, so now going back to these functions, I was saying we can use this induction on the depth, on the birthday, in going down the tree to define functions, and all these functions we find are canonical in some sense. There are concrete ways of doing this, so maybe I will squeeze these in the talks, in the lectures. So we can put a partial order on functions, and then we can say that these functions are the minimal ones according to this partial order. So the minimal ones that satisfy certain properties. So I can say, for example, the sum is the unique minimal, so actually minimum function, which is increasing in both arguments. So a statement like this. So there is a characterization that tells you, yes, these functions are nice in the sense that they are the only functions with a certain characteristic. Okay, and another sense in which they are canonical is that we're not using the axiom of choice. This is really inducting an explicit construction, not in the sense of computable, but it's explicit. You can do this without the axiom of choice. And the nice property you get is that if you take plus the sum we said it's a divisible order of the Abelian group. Sum and product is a real closed field. Sum, product, and exp is elementarily equivalent to real exponentiation, so it satisfies the same first order formulas as exponentiation on the reals. Okay, and this is the I would say the strongest way of saying that this exp as defined by Gonshaw behaves in the same way as real exponentiation. So for example, it's going to satisfy the obvious things. So e to x plus y is going to be e to x times e to y. Exp is going to be surjective over the positive real serial numbers, etc. So it really looks the same. And same goes for the restricted analytic functions. Okay, so we know the model theory, so we know an axiomatization of this structure, and boom, we can verify that it's still these canonical functions satisfy the same axioms. So you get an elementary structure which is elementarily equivalent to R and exp. Now, a common feature among these examples is that all these theories or all these structures are minimal, and which is nice. And actually, even more. I mean, these are all model complete structures in the language that we have written here. Which is even nicer. So model theorists know what I'm talking about. The other ones, you heard model complete in the previous talks a few times. It's a nice thing to have. And for example, I mean, just to make a comment which makes sense to maybe half of the audience, since the order underlying the serial number, so the dense order is saturated, and these theories are minimal, then what we're getting is just most and models of all these theories, because they're all saturated, even in new language. Okay, just a comment, just to say it's a huge model. Actually, maybe this makes sense for now more to more people. This, for example, means that every model of each of these theories, so the standard one, but also all the non-standard models you can think of that are sets, they can be embedded into serial numbers. So they're universal in this sense. Okay, now this universality is for the structures is the thing that I sort of want to justify for Transseries. Okay, I see Alessandro is making a good point in the chat. Thanks, Alessandro. So I repeat this for the recording. Is that one example of a thing you can do here? Exp is a global function. Okay, there's a global exp on serial numbers. So I can define exp of omega. But here I was talking about restricted functions. If I take the sign, I can perfectly well define in a canonical way the sign on the interval between 0 and 1. But this doesn't quite give me the value at infinity. So I go to omega, my sign is oscillating, and now the value in omega is not determined. Okay, so this construction that I'm referring to in this slide doesn't give you the value there.
But Vincenzo, you have
Yes.
the sign on all the real line or not?
Yes.
Yeah,
Yes, you
okay.
can. Yeah,
You
yeah.
can, okay.
Yeah,
And-
I mean, the caveat, the model theoretic caveat is that this statement, you take the restrictions to compact subsets, but this is a model theoretic thing that you have to be careful about. Yeah, no, but the sign function, you can take, you define it, you can define it over an entire real line. That would make perfect sense.
because it has a infinite radius of convergence or something, or is it another reason?
No, it's just that at this level, if you don't think about model theory, this is just you're constructing a function on larger intervals, and the union of all these functions is, you keep doing continuations.
Yeah, okay.
And that's fine.
Yeah,
that's
okay.
fine. The problem is you can't continue from the real line to omega because there's a gap between them.
Yeah, sure.
Yeah.
I understand. Okay, thank you.
Yeah, actually, there is a subtle issue below this, is that this is a non-Archimedean situation. It's totally disconnected. So when I said the word continuation, that's iffy. So, but yeah, I don't think that there's really well, there is some form of theory of analytic functions on certain numbers, but the theory of continuations is a bit different. Okay, now there's something funny here, but maybe I don't want to. Okay, I see that someone I don't know actually. Yes, one can define a super complex field. Yes, so the comment I want to make is related to this, so I can join the two comments. Is that, I mean, actually, there is a way, if you really want, there is a way of defining a canonical quotation marks sign function over the surreal numbers, and this actually was mentioned in the paper that is cited somewhere in this talk. So omega especially is the youngest infinite positive number. So I can decide, well, the sign of omega is 0 because omega is the youngest one. So I start from there, I put 0 there. So in a sense, I can define a canonical sign everywhere. And now joining this to the comment in the chart about complex field, I can adjoin the square root of -1 to serial numbers and formally define the sign of a formally defined complex exponentiation by using this kind of sine and cosine that can define in this way. Why don't we actually do this is that you're not getting an elementary extension of the standard models anymore. When you do this canonical extension of sine, the kernel is going to be of the form. It's going to be a discrete subset of a no, but you're not getting a non-standard model of the integers, for example, after you divide by 2 pi I. I mean, there are some things you have to do, some technicalities about, but the thing is, this discrete thing you see on the real line, when you extend it in a canonical way, you're not getting a standard an elementary extension anymore. Because, I mean, the underlying reason, it's vague, but it's that you're very far away from the nice model theoretically tame situation here. Yes, exactly. So you lose on minimality. And I would say that losing on minimality is it should be part of the reason why this doesn't work anymore and you're not getting elementary extensions. But it's not a formal statement. It's more of a philosophy that tame structures over the reals are the ones that have a chance of having these canonical extensions to surreal numbers. But the integers are not tame, and so they don't. Okay, so now we have this nice structure. So all these functions, and I want to move to now something a bit more technical, but hopefully now closer to the Transseries business. Is we have exp, but there's even more we can do on surreal numbers, which is we can represent them as infinite sums. Okay, as they also have a representation as exotic expansions. Okay, so let's see. Okay, so we start with something very, I think, traditional. We have an ordered field, and we say the two elements are in the same Archimedean class when they're not too far from each other in this sense. So x in absolute value, so make it positive. Okay, if it's negative, you multiply by -1 to make it positive. If the absolute value of x is bounded by some integer, multiple of y by some natural number, and vice versa, y is also bounded by a multiple of x. Okay, I'm using the same x to save space on the slide. the same n, the same natural number, but that's okay. What happens in the reals, everything is in the same Archimedean class except for 0. In the surreal numbers, you get much more stuff. So omega, for example, is infinite, is not Archimedean equivalent to 1, and it shouldn't be, right? While omega and 2 omega plus 1 are Archimedean equivalent because, of course, omega is less than this number, and 2 omega plus 1 is less than, for example, 3 omega. So they're sufficiently close to each other. Okay, and then I call group of monomials a set of positive representatives of these equivalence classes that is closed under multiplication. Okay, so I take my field, I split it into Archimedean classes. Each Archimedean class is made of 2 convex sets, one positive, one negative. And I want to pick an element from each of these convex classes. Okay, I take a set of representatives, but I want it with a special, I want it to be a group. I want this set of representatives to also be a group. And maybe I should rather do an example. If you take this ordered field where the variable t is, I mean, in this case, you can choose, I can choose t to be positive infinite or positive infinitesimal. You know your own preference. But in this case, the powers of t are all in different Archimedean classes. Okay, so t is much greater than 1, or smaller, depending on your choice. And it turns out that now if I take all the powers of t, these are also a group. And they represent all the Archimedean classes of this field. So this would be a group of monomials for the Laurent series. And of course, if you think about the Laurent series, these are infinite sums, and that's we call them monomials because they are the things that we sum together. Okay, in surreal numbers, we can do the same. Now there's a trick. These Archimedean classes are made of convex classes. Each equivalence class is made of 2 convex pieces, one positive, one negative. And so I just, since these are convex, I just say, well, let's pick the youngest guy in the convex class because we can do this. It's always this idea that there is this birthday gives me a canonical way, a way of choosing a special element. And in this situation, you can easily do that. So I take the youngest elements in the classes. This is now, these are 3 examples. One is the youngest positive surreal number in absolute. So it's definitely going to be the youngest in its own Archimedean class. Omega is the youngest infinite. So it's going to be also the youngest representative of its Archimedean class, the youngest element. And the same goes on for omega square, etc. And then what happens, and now you start seeing why surreal numbers are nice, because things sort of click together nicely. This class of youngest representatives is a group. Okay. So the product of, if you take 2 Archimedean classes, you take the youngest surreal numbers in each of them, you take the product, and the product, for reasons, is the youngest element of the other Archimedean class that you find. Okay, this is not trivial, right? I mean, there wouldn't be, in theory, in principle, there's no reason for this to happen, but then since the product was defined by using this induction, and it's the simplest function with certain properties, this makes things fall in place when you do these calculations. So after the fact, you become familiar with this, and then usually you can anticipate why you might get nice behavior. So what happens in this case is that you can construct manually the way people, I would say how people notice this, how Conway noticed this, is that there is a bijection between surreal numbers and the representative of the Archimedean classes. Again, and again, this is a function we build by induction. Is I send 0 in the youngest positive element. I send 0 to 1, and then I say I want omega of 1, which is the next element, to be in the youngest element in the next Archimedean class I can reach after the one I've already covered. Okay, but sorry, I'm getting carried away. I don't want to talk too much about this, but this is a trick you can do for several equivalence relations. So we will see this in the course. And this function is nice, and you discover, well, it's like an exponential function. Okay, and in particular, the image must be a group. Okay, a group which is isomorphic to the additive group of surreal numbers. Okay, so there is a nice choice of representatives for the Archimedean classes, which is a group. Now, when you have a group of monomials, at least in what I do, I have a group of monomials. I use it. I use it to do infinite sums. Okay. And again, oh, thank you. Mikael points out that this map omega is not just a group homomorphism. It's an ordered group homomorphism. So it preserves the ordering. So biggest serial numbers go to bigger Archimedean classes. Okay. I'm not going to use the function omega though. I try to stick with just the ordinal omega as much as I can because it's okay. So going back now to this, suppose I take a decreasing sequence of monomials indexed by some ordinal alpha. Okay, so for example, think if alpha is just the ordinal omega, I'm just taking a sequence of monomials which is decreasing in the more classical sense. I also take some real numbers, and then I want to make sense of this. Okay, because formally, like in Laurent series, you can do this kind of sums. I mean, Laurent series by definition are sum of powers of t multiplied by some coefficient. I want to do the same here, and again, I exploit the fact that we have this tree structure to make this kind of definitions. So I work by induction on the ordinal alpha. The sum up to alpha is what? If alpha is a successor ordinal, it's just, you know, the previous sum up to beta plus the last term. Okay, trivial way. Sum up to beta plus 1 is just sum up to beta plus the extra term at the end. When alpha is a limit ordinal, that's where the thing is more delicate. Well, I look at, I want this x, if I want x to be, to correspond to this sum in some way, I want these differences to become smaller and smaller. Okay, oh, I forgot the real coefficient. So there is a typo on this slide. There should be I here. And I think I probably overdid it with the, no, okay, this should be fine. Yeah, this is okay. Okay, I think people may, yeah, thank you, Alessandro, for all beta less than alpha. So if alpha is a limit ordinal, so in the Archimedean setting over the reals, this would be I'm defining the limit of all the finite sums, longer and longer sums. In the non-Archimedean setting, the limit is in general is not unique, but I can take the youngest limit, you know, the youngest thing satisfying this property. Okay, and this gives you a well-defined way of taking a series of monomials multiplied by coefficient and giving back a surreal number. Okay, and for example, I can define this infinite sum here. Something like this. This is a genuine sum that fits into this framework. It's indexed by an ordinal. The monomials are decreasing, multiplied by a real coefficient. Here the coefficient is 1. And I get this nice, you know, I can compute this surreal number. And now the nice thing is this behaves well in the sense that it respects sum and product, for example. Okay, and more precisely, what I want to say is that if you now think of these as formal objects, so not as taking some series and getting a serial number, you take a step back. If you think of this as a formal sum, and so this would be an element of a large Hahn field, the field of formal power series with some group of monomials, then serial numbers are isomorphic to precisely this. So what this is saying is that you can pretend that the serial number is just this formal sum, a formal sum like this. Because, for example, two different sequences are going to give you two different serial numbers when you take the sum. The sum of two sequences, it becomes is the same as another sum that you can make by you know, reshuffling the terms of your two series, and maybe summing the coefficients term by term. So algebraically, you can just work with this. Okay, so you can forget about the tree or serial numbers, all these inductive definitions, and think, oh wait, I can just work with this kind of elements. Okay, and so serial number can be expressed as a sum like this. I'm going way over time. And when we write a serial number in this way, we call this the normal form of the serial number. Okay. Okay, so now we're getting in business with these Transseries, because now I'm saying, okay, we have exp, we have log, we have sum and times, sum and product, and there is a structure of power series. Okay, so the two things together, they suggest Transseries, at least if you think about Transseries in an abstract way. So now in what way? Let's make this precise, actually possibly too precise. So I'm going to do something that I hate when people do it, but I'm going to skip over some details. But let's see this abstract definition. This comes from the thesis of Schmeling. I would say this should be attributed to Van der Hoeven as well. I mean, Schmeling was a student of Bresset and of Van der Hoeven. Anyway, in this thesis, you have a nice abstract definition. Though, whenever you take a Hahn field, so a field of Hahn series, power series, not necessarily the serial numbers, and you do have a log function, so your logarithm in the sense of the partial homomorphism, and you say this is transserial when, and you have certain conditions. So you want the function now domain, you want to actually to be all the positive numbers. You want the logarithm of the monomials to be just to be serious with infinite monomials. Okay, something we call purely infinite. Why do we do this? Well, because we want then the logarithm of these kind of guys to be given by the real logarithm on the real elements, and then we want the Taylor series of log of 1 to plus epsilon to be the thing that gives me the logarithm here. Okay, this we can do because when epsilon is very small, this power series converges in a suitable sense inside this kind of fields, and so it makes sense. So we can just use this as a good definition of log. Okay, now the tricky part. So these are sort of details which are easy to justify. I'm going to sort of skim over and say this is something we can ignore for now. It's reasonable. The last one is less reasonable, I would say. It takes some thinking. So take a sequence of terms in the sense of I take monomials multiplied by a coefficient. Okay, and suppose that the sequence is of this form. Each successive term, so mi plus 1, r by I plus 1, appears in the logarithm of mi. So I take the monomial mi, I take its logarithm, this is a series, and then I look at the terms appearing in its sum, and I want mi plus 1, ri plus 1 to be one of those. Okay, and now T4 says whenever you do this, whatever sequence you take with this property, eventually two things happen. The coefficient must become plus or minus 1, and the monomial and the term must appear last in the sum. It must be the smallest term of the sum. Okay, that's it. I mean, the first time I read it, I was like, okay, whatever, like you want to have this, but there's a sort of then digging to the literature, it start making more sense. So I was writing a justification for T2C3, but I want to skip it. Sorry, I apologize. I will send you the slides if you want to see it. Now let's look at T4, because T4 is kind of the technical thing that is mysterious, but then it's nice. It really helps. So the thing that happens is that, for example, you may have this a series like this. It starts with a monomial, and then there's another monomial. But if you dig into this monomial, so you write it as the exponential of something else, then you find another series here, but the series is of the form monomial plus another monomial. And then you continue like that, but there's always nothing else on the right. So what's happening here is that if I take this sequence M0, M1, M2, etc., well, sorry, the sequence would be this monomial. Okay, I choose poor notation. So the sequence would be this monomial first, then this monomial first, then this monomial first. This sequence satisfies both the conditions required in T4 in the sense that the coefficient of each monomial is just plus 1, eventually in this case, right from the start, and the monomial is always the last one. So this is okay. Whereas this one is not okay. okay? Because so these are sums where I have one monomial here, one monomial at the end, and one monomial in the middle. And then when I go here, I still have one monomial in the middle, and then another one. What's happening here is that I'm violating this requirement that eventually the monomial becomes the last one. Okay, so you don't want to have this behavior. Why? I think that the reason is that this is the kind of thing you would see in constructions that were done when studying the model theory of exponentiation. Especially I'm thinking of these two papers, because there are approximation procedures where you do get these sort of nested expansions where you first have a series and then you take the last term and you look at the exponent and you do an expansion of the exponent and you continue. What happens there is that you do get only this type of expansions where eventually you're always sticking to the right and the coefficient becomes plus minus one. I think that that's the origin, sort of the inspiration for this, but I think so. Maybe there's another reason, but this is what I understand. Okay. Now what happens is that certainly the field of Transseries, the one
Vincenzo,
yeah.
just sorry, isn't this n0 at the end of your expression, or you put exponential of n0?
Well, in this case, it doesn't matter, but yes, you're right. I wanted this to be
n1,
like this,
and then voila. Yeah. Okay.
Yeah.
Thanks.
Yeah. In practice, it doesn't make a difference, but it is but this was my intention, definitely.
Sure.
Yeah. But because the thing is the sequence of monomials in the middle is the one that is causing problems, because it's a sequence of monomials that is never the last one. It's always in the middle, and that refutes this and causes problems. Okay, so I think I should try to now sort of reach a conclusion, sort of make this visible. There is an abstract notion of Transseries, a Transseries field at least. The field of Transseries T that the Lau was talking about, that is model complete, etc., is a special case of this. So it fits into this definition, definitely. And now the complicated thing is, technically complicated to prove, is that surreal numbers do satisfy this property. Okay, so they are a Transseries field in this abstract sense. And the reason is that there is a procedure of chopping a surreal number, and the crucial thing that we prove that is really technical is this one, is that this procedure makes the surreal number younger. Now, let me show you an example. Rather than sticking to this definition of chopping, is more, how does it work? Start with this surreal number here. Say, suppose you have this one. In the end, you don't, but suppose you have it. Now, chopping means I cut off the last term here. Then I look at the last term of what is left, and I cut off the last term of the exponent. And then I cut off the last term of the exponent of the last term here. And I keep removing those guys. Now we proved in surreal numbers, doing this makes you younger. And since the birthday is an ordinal number, you can't get younger infinitely many times. Eventually you have to stop. And that's the thing that forces, that tells us that T4 is satisfied on surreal numbers, okay? And then there is another side of things, which I don't think we're going to prove in the course, because it's, I don't know, maybe there is an easy proof now, but the paper, it's a sophisticated proof for now. And I wouldn't be able to prove it. You should ask them, the authors of the paper. But then things go the other way. Every time you take a Transseries field in this abstract sense, there is an embedding into surreal numbers, which respects the Transseries structure. So it sends monomials to monomials and infinite sums to infinite sums. So this sort of justifies, I would say in a strong way, that no is the universal field of Transseries in this sense. Now let me cut to the very end. I had the slide on derivations, but well, let me show you one line of this slide, and then the final slide. And I promise that I will stop there. Yeah, because I'm really out of time. Okay, so to conclude, one thing is now serial numbers will contain a copy of Transseries, even just because they're universal in this sense. But in particular, you can build a copy in this way. Start with R omega, so just the field generated by R and the ordinal omega. And then you take the sequence of sets, and you just close the previous set under infinite sum. You take the previous set, you add all the exponentials and the logarithms, and then you close under infinite sums. And then you take this union, and this is T. So now this is my definition of Transseries. Okay, careful, carefully crafted definition. I just take this one. This happens to be a copy of T, and actually it's the canonical one. Okay, but it's not the only characterization, but there's another one here. Okay, now the final thing I wanted to say is that now what's happening right now, of course, in the talk in the course we talk about derivations as well, how to construct them, and how to get because you get a non-standard model of the differential field of Transseries as well. But now the final thing I wanted to say is rather what's happening right now, which unfortunately we're not going to talk about, but there is a lot of progress on this conjecture that actually I know is isomorphic to the field of hyperseries. Okay, for example, I'll try to say this very quickly and then conclude, is that, for instance, you can define the omega iterate of log. Okay, what do I mean by this? What do we mean by this is that we want a function like this. It's monotonic, okay, it's increasing. It's slower than any finite iteration of log. And then you want it to satisfy this nice functional equation, which I think people recognize here. Log omega of x is just log omega of x plus 1. So it's killing off iterations of x, making them become translations. And you want this to be analytic. In this case, that would mean have an expansion like this. So I want the derivative of log omega to be 1 over the product of all the finite logarithms of x. Okay. I want something like this, which makes sense only when x is actually positive infinite, because on the reals, this product doesn't make sense. If you do too many logs, you become negative, and this just doesn't work. Anyway, yes, we can build the simplest function with this property. And now this is a small piece of the picture. Okay, this is the piece where I was involved, but now there's much more. You can define, apparently people can define, but some can confirm log alpha for any ordinal alpha, and there is a set of rules very similar to these ones, and these functions are canonical. And I understand that now the picture is becoming very close to this general statement that surreal numbers are really a huge field of power series with x log, and also this transfinite iterate. So these very fast and very slow functions. All right, thank you for bearing with me to the end. I'm sorry I was slower than I expected. Thank you very much. Stop here.
Okay. Great. Okay. Any questions? Great.